This kind of looks like a mess, but I think I'm done. Yesterday there were some problems. The resistor blew because idiot me put it back wrong. Like I put it back so the resistor hit that, and then it burnt out that fuse. I had to replace the fuse because I placed it in wrong. Just as simple as that. And it's really elaborate, and it looks like junk, but it's electromagnetism. So we'll first spin the wheel to since we connected it. I want to document if I'm right or not. So we'll spin the wheel to see if it spins, and then we'll put the charger back on to see if it's charging, because it wasn't before for a while now. Wow, that's a lot of power. Uh, Everything works great. See if the light turns on. That's good. So we had a situation where sparks have occurred, even in the past, even before. But that's only because of my tampering. Like, when you have to readjust something or replace something, you'll spark it up. Just by replacing something, it will spark. Because this fucking green resistor, it's always sparking. Like, it's a lot of power in there. You have to keep it away from everything. So it's quite dangerous. Yeah. See that? It's, yeah, that's a lot of voltage right there. So I'll put my shitty camera here to show you the voltage. Fuck. This is a lot of power, basically. Notice how it sounds not like a weak electric moped that I've been using for the last 3 months or so. I don't know, but I've been using that. That's why I didn't notice. Like if I replace a transistor, I'm gonna spark this thing. I'm gonna think nothing of it, and I've done that many times. Like it's countless. That thing always gets in my way. Like whenever I take anything out, I hit that thing. So I put this in a better, much better place now. It's nowhere near the other items. Like I tie strapped it. Really annoying. See that? That alone is holding 26 volts. That transistor right there is holding 27 volts. Or, the whole voltage on one side and the remainder voltage on the other. That's 26.9. And we have to follow the gray cord now. This is like really retarded. It's very dangerous, but like you don't want to use old batteries, do you? You want to use new ones. So now we're gonna have to look for that stupid it's like a screw connector. There's a fan the coil system. It's wrapped for obvious reasons. I touch everything. where is the round object? There it is. There's a screw. So now you touch the screw to see how much voltage that is. Yep. It's reading good. .27. So it depends on what connector you touch, though. Like this will be that will be 0 volts. Yeah. Damn it. Shit. So to the negative of the terminal, it's actually 40 volts. Yeah. So the negative terminal to the positive is 40 by 6. See that? So that's like 6.6 volts, 6.7. And when I touch that side, 40. So 40 volts is actually charging at a rate of, it's charging over 6.7 volts. So that means it can go really far. So I'm charging 40 or whatever that terminal is by 6 volts. So that 6 volts is a part of a battery that's gonna be charged while I'm driving. I'll get basically a good 40 by 6. That means 40 volts would be charging 6 volts. That means 40 volts would be charging 6 volts while I'm driving. That means I would be getting a good 40 by 6 volt charge. So 40 volts will be inducing on the 6 volts at about precisely 5 watts. But there's no 6 volt battery. Get it? We have to use a an AC current to make the battery into 6 volts. So it'll be charging while I'm driving. But because it's connected to the grid, it's 40 volts. So I think let's disconnect it from the grid and see what it is. So while I'm driving, it's going to be 20. It's going to be 40 by 40 by 40 while I'm driving. Not 40 by 6, mind you, just 40 by 40. When it's connected to the grid, it's 40 by 6. Due to the fact that it's going through the circuit via higher amperage. I'm not actually sure. I'm not actually sure. 27 by, so that's 27, and then we touch this gray wire, which is going to the joint. Okay, I get it. That's 27 flat. It's not 27 flat. $27 by, really? They say we're reading the voltage. 27 flat. So that's 27 flat by 26.9, not exactly 27. So I'm off grid, it's going 26.9. So this side of the resistor will fluctuate to 26, and that one will stay at 27 volts. So it's 26 by 27. So I'm getting like a 0.1 volt draw. Of induction. That doesn't seem like a lot, but that's the laws of induction. It has to be equal on both sides. Otherwise, we'd already invent electromagnetic cars. It's more like a Kirchhoff law. That means both sides have to be equal for induction to occur. Off grid, of course. Why is it 40, or 27 is an example, but 40 is the actual example. So that's the 40 signal right there, and that's the 27. That's easier to reach. So let's try the 40 signal to see what the voltage says. Zero by zero. Interesting. And let's see what the other signal says. $13. 0. That's 13 volts. So 27, 13. 13.4. 13.4 flat by 13.4 flat. So that's not induction. It's not. So I got 13.4 here by 13.4 on both sides of the resistor. Right here, I got 27. Sorry, I got 0 right here. So this is always 0. This is choked out. That's 0. That's 14.4 flat, and that's 26.9 by 27 flat. 27 flat by 26.9. And that's the laws of induction. It's just you're just exchanging a very equal number, off grid. So you have to make the coil shield an electromagnet current. That means, see that fan right there? That's our AC current we're working with. So we just need a current that goes back and forth for the capacitor to charge, which is a 35 volt capacitor somewhere in here. And you just, you make a 100 volt coil to create DC again. So it goes, I'm not actually sure why I have a 100 volt coil, but that's a primary and that's a secondary, or whatever you call it. And that's around shield around the coil. So I don't know if it matters if it's taped or not. I just taped it so that it won't hit any like terminals, which it done multiple times. And even though that resistor was burned like multiple times, it still reads like it's still it's not defective. I don't actually know what type of resistor that is. That's confidential. But I think it's it's basically you can actually use any resistor. That's just acting as a capacitor, basically, as a mild capacitor to to divide the current, you could say. Like it's a meeting point for the current, and it can literally be any type of resistor. It doesn't have to be. It has to look like that or something. It just has to be a way for it to meet the 2 points, the negative and the positive. So one point, see that one side goes directly to the joint, while the other side goes to I think I'm finished. The other side goes to a coil system. I have to look at the diagram because I don't remember and I can't really see where it goes. So let's look at the diagram on my computer. I'm done, actually. That was hard work. Yeah. Oh, let's plug it in. Oops. I don't plug it in for. If you plug it in, the volt changes, which is good. You want that 40 by 6, because then you know that the 6 volts is the AC current side. it just transitions with with a higher amperage. It'll transition to 6 volts. Uh, but here's the diagram that I'm talking about with that I always look at. It's basically what Area 51 would do for if they had a vehicle that could recharge while you drive. It's no secret, basically. Um, Alright, alright. Goddamn computers are slow. Um, they actually, control computers through Explorer somehow, so sometimes it's slower. So this is a diagram we're following. Oh, it's right there. I actually don't even understand it. That's why I'm always testing it. I don't know the laws of electromagnetic induction yet. Like, I accidentally stumbled upon it. Like that system right there that you just saw, it can run a 12-volt fan for like infinite, like without decharging the batteries off grid. Wow, that's slow. Like hello clock. Anyways, so I don't have a better resolution for this. But that's the diagram I'm following. And this is actually this capacitor right here. So this is doing the same thing. But it's like a test capacitor. So it will do what this capacitor is doing. You could actually put this negative and that positive there, and you could actually joint it there and test this capacitor. It doesn't matter. It's just that this capacitor is very inaccessible. This is a 35 volt. So that might give a different reading. I remember it did, but I'm not sure. So if the last time I tested it gave no readings. So it was right here. Like something exploded here. Like I always touch something and then that will burn out this wire, or it will burn out. It will actually even burn out the inductor right there. So that's an inductor. Those are the two main wires that always likes to burn out, because those are the two main wires that are connecting the positive with the negative of the circuit. It doesn't like to burn out this AC current. Like this AC current's actually fine. This is a primary and this is a secondary, and I'm actually converting it to get the I'm making the current go back into the coil, and at that rate, it's going through here. The arrows mean nothing because I don't know what the current does. But this is an AC current, I know that. And this is a DC current. So we're working with DC to AC, and that's the joint where they both meet. So, right here, this joint of the resistor we're testing is exactly well on grid, well on a charge. Is this? Anyways, well on a well on the voltmeter, it says right here 26.9. Right here it'll say 27 flat, and that's induction. Believe it or not, it's a form of Kirchhoff's law. Both sides have to be equal for induction to occur. It's also Faraday's law. That's a 5-watt resistor, so that's very important to you don't want a lot of energy inducing, so inducing the current. This will always be 0 off grid. We choke this out. This is always 0, believe it or not. On grid it's 40 volts, but off grid it's 0. So why does it change when the circuit's on grid? Very simple. The circuit changes when it's on grid because it changes to 40/6 on that particular transistor, like you just saw, because this side, the 6 side, is going to be reading from what the fuck? This side is going to be reading 6, right? So obviously I have no idea why it does that. Like, I don't know why it changes when it's on grid to a different voltage setting. You could ask me, but I put a thermal fuse. I used to use a fuse there, like a 30 volt fuse, 32 volt, whatever. I used to do that, but I changed it to a thermal fuse because they work a lot better. So the fuse actually blew out just like I was playing back last night, and it blew out after working on it for 3 hours on tests. I was just gluing things, soldering connections, welding connections. It was fun, but I did make a mistake in the end, and it doesn't matter if it's a 50-degree fuse or an 80-degree fuse, but it's generally a wash machine or a dryer or even a microwave might have those thermal fuses. They just act as normal fuses. All fuses control amps. They don't, like, the volts don't matter. It's actually the amps that matter on the fuse. So the higher the amps, the better. So these fuses right here can contain 25 amps at at 50 degrees. But if you can get one at 80 degrees, it's better than hold on. Like I used to use a 32-volt fuse with like a 6 amp draw or something. Those don't work. You can't have 6 amps for EMVs, for electromagnetism. They'll always burn out or something, or they'll blow up the wire. These dinky fuses don't work because they don't have lots of amps. I was actually using this one and it blew out. This one's a big one. This one worked really well. But idiot me put the connector down and the connector blew it out instantaneously. It must have rested on it for it to do that. So there's some sort of current going there. Disappointed, right? See how dinky that amperage is? That will blow out. That will definitely blow out. So you need something like a thermal fuse with anyways. Volts don't matter. Like fuses just need you just need the amps for the fuse. So I'm looking for a thermal fuse that's what it is. So these carry about 25 amps. They get a lot of amps. You know, a common washer dryer fuse. I don't really have specs for it, but I already know what it does. I'm trying to see some specs for it so I can see the difference between a big one and a small one. This one might carry more amps, basically, and which is good. But anyways, theoretically, though, you just need one, you know. And you know, you don't want the moped itself doesn't do a 36-volt moped has it's so weird. My stupid keyboard is lighting red, like around there, like it's blinking red. Anyways, I don't recall any red lights on this keyboard. So, we have to go to a volt amp calculator because I don't know how to do what I'm thinking right now. Say you have 5 watts with 32 volts. Wait, what did we read again? We read about 27-volt draw. That's going to be like very low amps. So that's going to be very safe for charging. But say you have something more powerful like our grid charge of 41 volts by 6 amps. So that's a grid charge right there. And we know it's like 6 amps. Did it just reset itself? Damn it. Thanks for the ohms. Anyways, 41 volts at 6 amps is 246 watts. So, electromagnetism is kind of like taking energy from the motor, like what your car does with a starter. It takes energy from the motor and say the motor's a stator. It's like having a stator on an electric vehicle, basically. It's like having a generator on an electric vehicle, but the generator is the electric motor. So my 36 volt is really low. My charging sequence is really low amps because obviously you need to charge it right from the motor. That was the idea, is to get the motor's excess of 0.45 volts and tune it up to like a motor has an excess of 0.45 volts when it's running, and that's what charges a battery on something. So we're just getting that excess of 0.45 volts. And, we're inducing it to something like 6 volts. We're making it bigger, basically. I studied this stuff for a long time. And I used to be able to charge a scooter with an antenna even. But this is much more conventional for me. It lasted for 4 years. So what happens is that the electrical, I wouldn't trust these marks. Like, these are not professional because I don't know what the red means. But the like this is AC, right? These are AC DC batteries. So we're getting electricity that's that's going out of the the motor, and AC will drain uh, it'll drain slower than DC. So you'll get AC, and then the motor it will what it creates will in fact like pretend that fan is the electrical motor on your electric vehicle. It will induce, you know, um, it will induce that charge. So that fan will run forever on these batteries off grid. But an electrical motor is more complex because it has a lot more energy. So it's not using all the it's not going to be using all of the charge. Yeah, that's about it. Like I think I'm done with that. Like I might use it a few more times. Well, I'm a big problem with them. With scams on the internet currently. Um, so that's basically it. To tell you the truth, I don't know how it induces it. To tell you, but this point right here. Now this point right here is gonna be 27 volts flat or 13 volts flat, whatever. But on this side right here, it will be 26.9. It'll be different off grid when you're riding. It might change like to a different number. I forget what exactly happens. And I don't know if the burn actually burnt out the resistor. Like I don't know if it was different before, but on grid it looks like it's correct. It looks like it still works. It's 40 by 6 or 27 by 6 or whatever by 6. So this side will be 6 volts. And I'm getting that number by subtracting 35 from 16. I'm just kidding. I don't know how I'm getting a 6 volt number. But that's 6 volts right there. I remember it always being 6 volts since I built it. Um yeah, so that's electromagnetism. It's actually a principle that's very, very hard to understand. Like if I had a voltmeter, it would detect the the battery. It would detect the vehicle off grid, like there's a shield around it or something. Maybe it's on grid that would detect it, but it would detect the vehicle. Like the electricity would go on the frame or something. So I don't see how that's weird or not, but it is. And I have this theory that that it's drawing electricity in actually, like it's sucking it up. But I don't know how to explain that. The the circuit itself is very 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 complex if you think about it. Well, this circuit will guaranteed will recharge your vehicle while you drive. The problem with Tesla doing that is, or some other car manufacturer doing that is, they're not. It's not gonna be possible for them to do that. They're not recharging. They don't have a recharging circuit. That means they don't have a way to get you know charging an electric vehicle back into the battery off grid. That means it's always on. And this circuit itself, well, if properly built, if put in if properly built or put as as a circuit board, it would, you could leave it outside in Siberia and it would still work. Um, Now, what's happening is very difficult to understand, though. The the voltage is is being induced constantly. That means when it's off grid, when it's off, it's being charged. When it's on, it's being charged. That's good. That's the circuit that I was looking for. But how is it induced? I don't know. As you know, off grid, this is 0. This we read earlier, or we saw earlier, this is a 0 marker. That's that will read 0 on your voltmeter. You know, um, uh, 27 and 13. 0, 27, 13. That's how a battery should read. So 0 to negative is off grid. 0 to negative. So you touch the negative terminal, 27 volts. 15 volts. Sorry. You touch the negative terminal. Sometimes it's retarded. 27 volts. 13 volts. 0 volts. That's how an electric vehicle should read. '27's way up here off grid. It's this battery right here is 27 volts off grid. This battery right here is gonna be at 13 volts, and this one is 0. And that's how you recharge an electric vehicle. So it is possible. If you were to recharge an electric vehicle, it's possible. And if you're to recharge a, you know, It's like recharging a gas vehicle, but you need to consider the fact that you're using you have to consider the fact that you have to contain the voltage that's coming from the gas vehicle when it's not isolated. You have to contain that voltage, and that's what I did. Otherwise, it would just be decharging from this terminal as 36 volts, and these batteries would last what, like 6 months? They wouldn't last a long time. Not with a 1,000 watt motor, no way. Um, they would last about 6 months, 12 months before they start decharging. I was accidentally using it actually, with it, with this circuit disconnected on these two joints. So even if these two joints are disconnected accidentally from a bird or whatever, believe it or not, it still conditions these two batteries. Not, oh, that one would be burnt out. Shit. Oh, that would actually be a big issue. That it would be isolated. So I was using an electric vehicle for like, God knows when. But it's supposed to be electromagnetic. Yeah. That would explain why it was running out of juice when I was going short places. Like it doesn't even go 3 miles with anymore. I don't know. Strange how you don't catch these things, but sometimes you just have to go and come back. Sometimes you don't want to work. Like when I put the new transistor in months ago, whatever. Like I must have touched something. So I got that transistor months ago. I must have touched something and, you know, this was off. This was burned off, and this was burned off. And I did a continuity check to verify it recently, and the continuity on both of these wires didn't. Yeah, it was burned off. Now, how did I invent this? I'm gonna say that I've experienced with antennas and stuff. So. But that's how electricity should work. It should work like this. This 12-volt battery should go up to 27 volts. This battery right here should go up to 13 volts. This one should go up to 0 volts from that point right there. So we'll go and test it again. But from that point right there, a 27 volt charge, a 13 volt charge, and a 0 volt charge. So we'll go and show you right now. Alright. I have to practice at doing this or else I'll forget. I don't want to go backwards, basically. $13.27. Yeah. And that side to that side. Let's just do that. I don't have to prove it, but I guess so. I guess I'll 13.7. Um, hmm. So we came across an issue here. Um, Even on grid, it's reading that voltage. I don't know. Maybe I spin the wheel and test it, but when you spin the wheel, it'll read at 40/6, I guess. On grid, like it charged something. But it's on grid. It's reading 27/0. So let me keep testing it. I just have to use it, you know. I don't know, I just have to use it, I guess. But yeah, 0, 13, and